Okay, let me continue the lecture. So, the last lecture we have seen that, well, first we looked at well, the notion of the dominated strategies as one solution concept, and we talked about another solution concept as a solution concept, the saddle point. Okay, so it's basic how the analyze the solution, how to compute the saddle point is that we sort of compute the saddle point, where in this finite case, how can we do that? Well, we draw the arrows depending on the goal of each player. For example, in this zero-sum game, the player 1 tries to maximize his payoff, but the player 2 tries to minimize the payoff. So with that goal, well, we can draw the arrows, and then we can see that, well, all the arrows are sort of concentrated in one point, and that should be the mathematically saddle point. I mean, if we do some math, okay. So saddle point is like this form. So we have talked about the saddle point, and some people can have a belief that if we were given that kind of game, then each player will behave such that it chooses a strategy to satisfy the saddle point principle. Now in this lecture, we're going to talk about now the why each player will play the saddle point. I mean, what is the rationale behind that? So that's we're going to talk about that. All right. So let's start. Why play the saddle point? So okay, we are given the same game. Here, suppose that I mean suppose that. So let's assume that if the player 1 believes player 2 will play B. Okay. We assume that. So if the player 1 believes the player will B, okay, why B? We're gonna talk about that later. Okay. And suppose that player 2 is playing the player B, then we are asking the question that how the player 1 will choose the strategy. Well, I guess the one of the obvious and natural and the rational choice is that player 1 should play C. The reason is that because the choosing C is the best response to B. Best response means that, well, if the player 2 will play the B, then my payoff means that player 1's payoff is the -1 for A, and 2 for C, and 0 for D. So obviously the player 1 will choose C, right? I mean, if the player 1 believes the player will play B, right? Similarly, if the player 2 believes that if it's player 2 will believe, so player 2, I'm talking about the player 2, and if she believes that the player 1 will play C, suppose that she has a belief that, okay, player 1 will play C, suppose that, let's assume that, then obviously player 2 will compare the payoff of these three guys, right? Like A, B, or D. Then obviously the player 2 tries to minimize the payoff, and she will play the best response to C, which is out of 5, 2, and 3. Because she tries to minimize that, they will play B in order to choose the minimum guy. And that's quite rational. Okay? But, right? Okay? So like this. Right? Okay? Now you have a question. What is the question? Why the player 1 believes that, where does this belief come from? Where does this belief come from? Or where does this belief come from? I'm going to talk about that. Why player 1 believes that player 2 will play B, or why player 2 believes the player 1 play C. So let's go deeper into the mind of the player 1 and player 2 C. Okay? Now, so that's what we have done. And now the question is that why should the player 1 believe the player 2 will play B? Okay, so suppose that you are player 1 and player 2 is your friend. I need to expect the player, my friend's mind, player 2's mind. All right. So in this case, you are thinking that, all right, player 2 will be, so player 2 will choose A or B or D. I mean, what is the criterion under which your friend will choose A strategy? Well, probably the playing B guarantees the player 2 losses at most V. It's like a minimum loss in some sense, which means that in this case, if the player 2 if your friend is choosing A, what is the loss that they will experience? The kind of maximum loss. That should be 12, right? I mean, remember, the player 2 tries to minimize that. Of course, it's possible that your friend can get a very nice payoff, minus 16, but that is based on the assumption that the player 1 will play D, but player 2 does not know what strategy the player 1 will choose. So player 2 is is trying to apply the safety rule, meaning that, okay, in the worst case, if I choose play A, then I get a 12 payoff in this case. Okay, right? That's the kind of maximum loss for A. If I choose play B, what's the maximum loss? Maximum loss will be 2. What happens if the player 2 would choose D? Maximum loss will be 3. So player 1 believes that, okay, my friend, which is player 2, will experience the maximum loss of the 12 if she chooses A, and the maximum loss of the 2 if she chooses B, and the maximum loss of the 3 if she chooses D. Then means the player 1 believe that, okay, player will choose the worst case safety rule, and then player will choose B, and that actually guarantees the loss at most V. It's like an 안전빵 strategy, right? I mean, the player 2 is should be very shy. So he does not take the risk of losing a lot of points. Okay, player 2 tries to guarantee that what's the loss of the worst case, at most case. So that's why the player 1 believes that, all right, player 2 will believe B, and then that's why I will choose C. I mean, this is the game. So we don't know what strategy will be chosen by each player. So I have a belief that. And the same thing, why should the player 2 believe that the player 1 will play C? I mean, remember the player 1 tries to maximize that. So they compute that, in the player 2's belief, okay, I'm a player 1. If I choose A, I can get a win of, let's say, in this case, 12, which is the maximum. Okay? Which is, actually, let me see. Yeah. If the player if player 1 chooses A, then I can lose up to the -1, right? Let's say here. If player 1 C, the lose -1 means that that's the kind of smallest payoff. If player 1 C, then what's the smallest payoff? That's 2. If the player 1 D will choose D, what's the smallest payoff? That's the -16. And the player 2 believes that, all right, player 1 tries to maximize the payoff. So she will choose the player C because it guarantees the the winning of at least V. I can guarantee that this is the sort of at least I can get a pay of 2 in player 1's perspective. So that's what the player 2's belief. Okay? Right? So player 2 believes that, well, player 1 will compute the smallest amount of the payoff they can get for each choice. Okay? Alright? And then player 2 believes that okay, player will choose the strategy that can guarantee that it that gives the wins or the money at least some value, which is 2 in this case. Alright? And that's what they believe. And this is the powerful argument that why the saddle point will be played when we run a game. Remember, the situation is that player 1 and player 2 cannot talk to each other. They need to select a strategy. And then somehow each player should have some belief about how other player will play. And the belief behind this running or the choosing the saddle point is as follows. So let me formalize this argument using a different game. Okay? Through which we can sort of compute, we can develop an algorithm which is called the min-max algorithm to compute the saddle point in a finite case. Right? So using those ideas of the playing the saddle point and why the saddle point, essentially what the player 1 and player 2 is doing. So the player 2's perspective, what they are doing is that for each column, they sort of compute the maximum entry in each column, which is in this case 7, and in this case 8, and in this case 2, and in this case 5. Okay, so what is this? What is this is that from the perspective of the player 2, he thinks that if I choose A, what's the maximum loss that I should pay? What's the maximum loss that I will be obtaining? That's 7, because I don't know which strategies will be played. So that's the maximum loss that I play A, and that's the maximum loss and maximum loss and maximum loss. And we compute the minimum, which he provides the sort of the losses at most 2 in this case. All right? Okay? So this is what? This is something called the minimax value, because I first compute the max and then I do the minimum. Right? And for the player 1's perspective, what these guys are doing is that they first compute the minimum. Now, what's the minimum of this? If player 1 chooses A, that's minimum is A. Again, remember the player 1 tries to maximize the payoff, and player 2 tries to minimize the payoff. So essentially, the 2 means that that's the sort of the minimum payoff that I will choose I will obtain if I choose A. That's the minimum payoff, because I don't know which strategy I play as a player 2. I'm sort of thinking about the 안전빵 strategy in some case. So these are the minimum, right? There's 2, and in this case minus 10 and 1 and minus 5. And then I compute the maximum value. So I do the maximum of all this, which is the maximin, right? Okay? And then if this minimax is equal to the maximin, and that is the saddle point, if you think about that, right? it's sort of a something like this direction and this direction and this direction. We will see that. So we can actually come up with some algorithm to compute the saddle point. But more importantly, we essentially this minimax algorithm is coming from our argument of why each player has a belief about how other players will play, and that's why I will choose this. So using that mindset of playing the minimax value and the max min value, well, actually each player will choose a strategy, something like here in the player 2 will choose C, and the player 1 will choose A, and that is based on the belief that I mentioned in the previous slide. And mathematically or the algorithmically, this is checking whether the minimax value is equal to the max min value, and that is the saddle point. And we believe that this may be a good solution concept. Well, maybe some people may not agree, but that's quite reasonable. Okay. All right. So I hope that you have an understanding about. I mean, we mathematically know what the saddle point means, but the question is why in this game each player will play the saddle point. And I have explained the sort of the mindset or the rationale of why play the saddle point, and that makes a powerful argument that the saddle point is a nice concept, nice solution concept in the game. Okay. There are many cases where we have a multiple saddle points. Okay, so here if you compute the sort of the maximum first here, and if you compute the minimum, then we have 2 points. And also here the first to compute the minimum, and if we choose the maximum value, that also two points. So we have 4 saddle points. That's possible. That's possible. Okay, so we have 4 kind of solutions in this game if we apply the saddle point concept. Okay, are there any games with the no saddle points? Obviously, if you draw the arrows in order to compute the saddle point, then player 2 tries to minimize that. So I have the arrows in the right direction in this way, and here in this way, here, and here. We have just a circling around. There is no like some strategy vector such that every arrows are concentrated on that strategy vector. There is no such things, which means that it does not include the saddle point. I mean, mathematically it's possible, right? I mean, saddle point is a very nice property where we have like a saddle shape of the point. So there exist games with the no saddle point. Okay, so that's quite also natural. Okay. So we have talked about so far the zero sum game. So in the zero sum game, we have talked about the strategy, dominated strategy concept, and the saddle point concept. Saddle point concept should be a pretty good, but again, there are some cases where we have multiple saddle point, where we have no saddle point, and so on. So I guess that's unavoidable. All right. What about the non-zero sum game, meaning that it's a more generalized game? Something like this. Okay. So if we try to the non-zero game generalization, and then we see something like this. This is obviously the payoff sum is non-zero, so it's a more general form of the game. All right. In this case, one may propose that, all right, what's the solution concept in this game? I mean, we have just talked about the solution concept for the zero sum game. So somehow we need to define the solution concept for the non-zero sum games. Why don't we play just a saddle point concept to this non-zeros game? Probably we can do that. I mean, this non-zeros game obviously reflects the situation where interest is not directly opposed. All right. There are many types of the games that we can think of. So why do we play the saddle point? Well, let's play the saddle point. And then what we are doing is that first I compare the strategies of in the player 2's mind. So I compare these two numbers. All right. Now player 2 tries to maximize that. So from 1 to 2. So we have this direction of the arrows. And then here in this case we are comparing these two strategies. these two strategies. So we need to compare this 2 and -1, right? So we have this arrow directions in the same way we have this direction, and the same way we have this direction. So this is a kind of setter point. All right, and probably we can make this a solution as a solution concept for the non-zero sum game. So this is a pure strategy equilibrium that we can think of. I mean, we need to formalize this concept for the non-zero sum game somehow. But let's look at the other example where even in this case there's no pure strategy equilibrium, also, which is also possible. So for example, here we compare this 2 and 1, and we are in this direction of the arrows because this is larger. And what about this? What about this? 5 and 3, and we have this direction. And here in this case 0 and 4, we have this direction. Here in this case -2 and 1 and 2 in this direction. Oh, just the circling around. So there's no like point, something like all the arrows are concentrated each other. So in this case there's no equilibrium. But anyway, if there exists a point something like this, right? Point something like this, then somehow we need to formally define that. So that's what John Nash's contribution. For the general game, he thought about how can we generalize this concept and tries to sort of mathematically describe the solution concept, and that's the Nash equilibrium, right? And Nash equilibrium is nothing but, in a finite game, it is nothing but something like this point. Okay, so let's now we have a very famous equilibrium, which is a Nash equilibrium. So let's parse this theorem, parse this definition, so that we can understand that. Okay, so Nash equilibrium is a strategy profile or strategy vector, if you like, S star, which is a vector of the strategies. Okay, this is a vector across all the players, with the property that no player I, this is a very important statement, no player I can do better by choosing a strategy different from S star, like deviation, given that other players are playing according to S star. Okay. Yeah, we should have that statement. Okay. All right. Do you understand what I'm saying? I mean, let's look at mathematically. So suppose that S star is a Nash equilibrium. I mean, S star is a S1 star, S2 star, Sn star, if we have n players. Okay, suppose that this is a Nash equilibrium, that it should satisfy this equation. So what is this equation? So I plug in the strategy of I. This is I's perspective. So I compute ith payoff of Nash equilibrium, and that should be larger than, okay, larger than this payoff, where this payoff is that I fixed the strategy of other guys except for I, and I change my strategies for all strategy choices. This payoff value is larger than this case, and this equation should be satisfied for all I. That's the definition. So it means that, so okay, so the question is that, okay, I claim that some strategy S star, some strategy Vex star is a Nash equilibrium. How can we prove that? Okay, you claim that some strategy S star is a Nash equilibrium. How are you going to prove? Well, how am I going to prove? Fix I, fix the player, Then I compute the payoff value and fix other payoffs, other guys' payoff except for and I change my strategy, I strategy, whatever you want, and make sure that this equation is satisfied. And we check that fact for all I. And if that is satisfied, then that's a Nash equilibrium. So it means that no user can change its payoff by unilaterally changing. This is a very, very important word. Unilaterally changing its strategy, which means that changing its strategy while other guys are fixed. Okay? So if the S star is a Nash equilibrium, I plug in the other guy's strategy as it is a Nash equilibrium, and I unilaterally change. I only change my strategy, and I have to prove that the payoff at the Nash equilibrium is larger than for any other kind of strategy value. I mean, any other payoff value for the strategies, where the strategies are in any choices that I can choose. That's what we mean by unilaterally. All right? Let's make some practice. So let's. I claim that this is the Nash equilibrium. So let's use the definition of the Nash equilibrium. Why this is a Nash equilibrium? Okay. So let's check that. So in player one's point of view, okay, player one's point of view. So I fix other guy's payoff, other guy's strategy as if. So I claim that A, A is a Nash equilibrium. Right? I need to prove that. So fix A, players 2's strategy, and I unilaterally change my other strategy. Here I just only have the 2 strategy, right? So I change that into B. Oh, the payoff is 3 here. In this case, this is payoff 5. So this is larger. That's the checking for the perspective of the player 1. Now let's check for the from the perspective of the player 2. So fix A here in this case, and then I unilaterally change A or B, and I compare the payoff of the player 2, 4 and 0. Oh, 4 is 2. So this is a Nash equilibrium. So A, A is a Nash equilibrium. I prove that A, A is a Nash equilibrium according to the definition of the Nash equilibrium, and then you will see that sort of the similar concept of the saddle points in the general non-zero sum game is actually the Nash equilibrium. Okay? Obviously, there are some games that there could be a multiple Nash equilibrium. So let's look at that. So what is a Nash equilibrium? Here, we can use the argument of the arrows, right? So out of these arrows, we need to compare the player 1's payoff because I'm talking about the A and B. I have this direction. And out of this direction, I have to compare 4 and 1. I have this direction. Here in this case, I have 1 and 2 in this direction, and I need to compare this 1 and 2. I have this direction. Oh, so this direction and this direction and this direction and this direction. So these two are the Nash equilibrium, like in this way. Let's check why this is a Nash equilibrium using the definition as I mentioned before. You can easily check that. So I claim that A, is Nash equilibrium, and also B, B is Nash equilibrium, right? Okay. All right. Why is that? So okay. So here, fix players 2's strategy, and I unilaterally change A and B, 1 and 0, and then 1 is larger, and fix player 1's strategy, I unilaterally change A and B, and I need to compare 4 and 1. That's exactly the argument, same argument as the, making the arrows, right? So we have this. So this is Nash equilibrium, and also similarly, this is Nash equilibrium. So obviously here in this case we have multiple Nash equilibrium. We cannot avoid that. Obviously those two strategy or the outcome is not same, so it's different. Yeah. And even it's not interchangeable, right? Because, it's different. the payoff is different, and so on. The value of the value is also different, right? This is 1 and 4 and 5 and 2 and 2 and 4 and so on. So we may have a different equilibrium. Now, you may ask the question, what happens if we have a 2 equilibrium? Then how the system behaves? You may have the answer like, okay, if we are stuck in this position, then we don't move, because that's the equilibrium. There are some cases where we are stuck in this point, we don't move. That's true. But the equilibrium is not talking about how we stuck at which point. It's just an equilibrium. They are not talking about the dynamics of the system, like from time 0, then I will go like, okay, if this is time 0, and I will go this way and this way and this way and here, and stuck. Or like here and this way, and then here, and I stuck. The equilibrium concept is not talking about such dynamics. I don't know what happens in the middle of the time, right? This is just a simultaneous game, and then we are interested in the identifying what's the equilibrium. I don't know what happens in the middle of the system. Okay? In order to talk about that, we need to talk about a different thing. I mean, this is exactly the same as the kind of optimization story, right? Suppose that this is some function that I'm trying to maximize that, and there are lots of local optimum, right? These are the local optimum, and all the algorithms in optimization theory, in this case, the best thing they can do is to find a local optimum. Whether it is this, or whether it is this, and whether it is this, and so on. Right? Otherwise, we need to do an exhaustive search. If we have to do the exhaustive search, then we can find the global optimum, but that's obviously not very useful. So what I can do is I just run something called the gradient-based algorithm, and it's possible, depending on the initial point, I can be stuck at this point, or I can be stuck at that point, or I can be stuck at this point. We don't know. That's the best thing that we can do, right? The key point that I want to make out is that, this is just the equilibrium concept. I'm not talking about whether I'm stuck at this point or this point. This is just a multiple equilibrium. That's it. Which is not a very nice sign, because this is exactly the same as this one. We have a lot of local optimum in some sense. Right? So before finishing this part of the lecture, I'm going to introduce a few famous games that actually has a different kind of features of the game. So first game is something called the coordination game, where the payoff is something like this. And the situation is that, suppose that you are in a road, like 2 lines, and then you have a car here. You have a car here in this direction. You have another car here in this direction. Okay? And these 2 drivers are driving toward each other. And then this is, let's say this is a car 1, player 1, and this is player 2. And if both of these 2 guys are choosing left, and left, they are fine. If both guys chooses right, then this guy will choose here, and that guy will choose here. There's no accident. Fine. But if this guy chooses left and this guy chooses right, and then there will be an accident. So we have a very low payoff. Okay. So it means that we need to coordinate with each other. Coordinate means that each player should choose the same strategy. In that case, we have a large payoff. And otherwise, we don't have any payoffs. Okay? What's the Nash equilibrium? Obviously, these 2 are the Nash equilibrium. Right? So we have 2 Nash equilibrium in this case. Another famous game is something called the matching penny game. This is a very, very famous example of the zero-sum game. And this game is well, okay, this is zero-sum game. So what's a matching game? we have two people, and then they show a coin. They have a coin, and obviously the coin has a head or a tail. Okay, and well, without any dialogue between these two guys, they show their coin head or tail. See, if the two coins are both head, then this player one takes this coin in their pocket. But if we have a different faces, like a head or tail or head, then player two will pocket them. Then what's the payoff of this game? Well, if both of the head, then player one will get payoff, but the player one will lose the coin, right? So that's -1. The same thing for the tail and minus tail. But if the faces are different, like head and tail, then player two will pocket them. So that's their payoff is 1, and the player one will lose the coin. So that's called the matching penny game. And that's exactly one example of the zero-sum game, right? What is the Nash equilibrium? Think about that. Yeah, please solve the game using the Nash equilibrium. You will see that. What's the Nash equilibrium? Another game is a little bit similar to the coordination game, but it's a little bit different. Here it's called the Battle of Sex game. That's also very, very kind of famous game. What this game is doing about is that, well, there is a husband and wife, and then in some Saturday night they tries to see a movie, but they have two choices. Like husband is trying to get some very, it's like a man-like movie. And one of the examples is Lethal Weapon. It's like shooting a gun, a detective story, a thriller story. And the wife tries to see the movie Wondrous Love. It's like some love story between a man and woman. Okay. Well, for example, right? So in this game, husband, I have a guest. Okay. Well, here in this case, well, each people has to choose or preference of the movie. Well, if they see a same movie, then there has some positive payoff. But the payoff is different depending on what movie they see. Okay? And suppose that husband chooses the lethal weapon and the wife chooses lethal weapon. And then the payoff, let's say, what is lethal weapon and what is wonder love? Oh. This is lethal weapon. Oh, lethal weapon and wondrous love. Okay, yeah. So wife chooses a lethal weapon. Oh, that's the other way around, because wife likes lethal weapon. Okay, that's interesting. Right, okay, maybe the wife likes lethal weapon and the husband likes wondrous love. Alright, sorry. Alright, according to this picture. Okay, whatever it is, I mean. Okay, so husband tries to see, okay, they need to choose a movie. So husband chooses lethal weapon and the wife chooses lethal weapon because the wife loves lethal weapon. Wife's payoff is 2 and the husband payoff, well, I have a more preference about the wondrous love. But it's good to see a movie together, so their payoff is 1. But what happens if husband and wife chooses different movie? Like here, husband chooses Wondrous Love and the wife chooses Lethal Weapon. Then obviously they need to go to a different theater, cinema. So their payoff is 0 because essentially the basic assumption is that they want to see the movie together because well, they sit together. Then obviously it's more fun. Okay. So when they choose a different movie, their payoff is 0. But when they choose a same movie, then the payoff is positive, but the payoff is a little bit different. For example, the husband chooses wondrous love and the wife chooses wondrous love, because the wife has a preference about the lethal weapon. So the husband payoff is 2 because he loves wondrous love. But wife, well, I'm not happy about the wondrous love, but it's good to see the movie together. So my payoff is 1. I mean, this is a battle of sexes game. And we have another very famous example of the prisoner's dilemma. And think about what is the Nash equilibrium. Like small homework is that, okay, what is the Nash equilibrium of prisoner's dilemma? Prisoner's dilemma game. Okay, think about that. So this is pretty much about the pure strategy. So let's sort of summarize what we have done so far. Okay. Okay. Here's the pen. Ooh. All right. So first, in this part of the lecture, we have talked about the normal form game. Especially we have talked about the finite case, where the finite means that the number of players and also the number of strategy spaces are discrete. Strategy spaces are discrete, and in this case we call it matrix game, right? Because it can be represented as a matrix, right? Oops. Oh, it's erased. Shoot. Yeah. Again. Yeah, maybe I don't know how to use pen in the PowerPoint. And matrix for the finite case and discrete case. Okay. Okay. So here we have defined the game, and we have studied the solution concept. Yeah, it's kind of, we need to identify what strategies will be played by the people, and we have two things. Okay, and we have first talk about the zero sum game because it's the simplicity form of the game. And then as a solution concept, we have studied like strictly dominated concept, and also we have seen the saddle point. I mean, the saddle point and the strict dominate concept can be applied to the non-zero sum game also. We have just talked about, for simplicity, the zero sum game. It can be applied to the non-zero sum game. Okay, so we have seen that, and we have seen that why, under what rationale. Okay, we have talked about the saddle point, and then we naturally extended this game to the non-zero sum game, and probably the saddle point is naturally inherited to the notion of the Nash equilibrium, which is very, very important, and we will see this word throughout the course. And all this solution concept, like we can have one, we can have multiple, even we can have no solutions. It's possible because the game can be quite different. What else we have done? Yeah, and also we have seen that examples of the game, famous game of games. Remember, this game is a simultaneous play. Okay, and we assume that it plays simultaneously. All right. So that's what we have done. Now, probably up to this point, you have a grasp of understanding about what the game is and what we are interested in and so on. So in the next lecture, we're going to talk about so here all these arguments are under the notion of the pure strategy. Okay, so what is a pure strategy? I mean, pure strategy is that it's a kind of deterministic choice of the strategy. Like, for example, suppose that I have three strategies, that I'm going to choose this guy for sure or this guy for sure and so on. Now we're going to extend to do something called the mixed strategy in the next lecture, where the mixed strategy is that, okay, I'm going to apply the probability distribution of the strategy vector. With some probability I will choose this, with some probability I'm going to choose that thing and so on. Right? So obviously the pure strategy is one of the special case of the mixed strategy, because I'm going to concentrate probability 1 to this strategy vector. That's one mixed strategy. Like probability is 1 0 0 0 1 0 0 0 1, where the mixed strategy is the 0.5, 0.3, 0.2, 0.4, 0.3, 0.3, something like that. I'm going to apply the probability distribution. That's the mixed strategy, which I'm going to talk about. All right, see you in the next lecture. Thank you.